Fractal universe theory. The concept known as the fractal universe hypothesis proposes that the cosmos, though immeasurable and extending across billions of light years, might not just be vast. It could be endlessly intricate, repeating its patterns at every level of scale, whether microscopic or cosmic. This fascinating idea stems from what we know about fractals. Fractals are geometric figures or patterns that replicate themselves across various scales. Take a tree, for instance. Its limbs split into smaller branches, which then divide into even tinier ones, each level reflecting the overall form. This recursive pattern means the structure appears consistent, regardless of how closely it's examined. Fractals are found all throughout the natural world: clouds, coastlines, mountains, and in mathematics. They embody a unique type of self-similarity. The fractal universe hypothesis proposes that this principle might extend to the entire universe itself, suggesting that structures repeat across different levels of reality, from the minutest subatomic particles to vast galactic formations. At first, the idea might seem too abstract, even implausible. How could such a massively complex universe be governed by a single, repeating pattern? Yet, some physicists believe that the fractal nature of the universe could offer explanations for certain cosmic phenomena that still puzzle us. For example, the large-scale arrangement of galaxies doesn't form a smooth or uniform distribution. Instead, galaxies tend to cluster together, creating immense voids and intricate networks that resemble branching patterns, strikingly similar to those found in fractals. This suggests that the universe may possess a concealed self-similarity across scales. What's perhaps most compelling about the fractal universe theory is its implication that, just as fractals possess infinite complexity, the universe might also be without a definitive edge or endpoint. Rather than ending somewhere, it may continue indefinitely, structures repeating infinitely whether we peer outward into deep space or inward toward the quantum level. This concept provokes deep and unsettling questions. Could the universe itself be a pattern we're only beginning to understand? If the cosmos truly operates on fractal principles, then we might be standing on the edge of a multiverse, each layer revealing another, forever. Though unproven, this hypothesis fuels a profound sense of wonder, pushing us to reconsider the structure of reality and everything we think we know. Whether or not we find evidence, the mere possibility invites us to look deeper into both the universe and ourselves. Levitating plasma clouds. Imagine standing inside a laboratory, gazing at an unusual, glowing cloud of gas that hovers motionless in the air. There are no wires, no physical supports, just a luminous plasma cloud, perfectly suspended. This is the baffling phenomenon known as levitating plasma clouds, a mystery that has challenged scientists for years. Plasma, often referred to as the fourth state of matter, is a superheated gas composed of charged particles, specifically electrons and ions, capable of conducting electricity. You'll find plasma in various places, from neon lights to lightning, and even powering the sun. However, generating and sustaining plasma within a controlled environment is extremely challenging, especially when that plasma begins to float. What makes this occurrence so perplexing is that, under standard conditions, plasma behaves like any typical gas, expanding and dispersing. But researchers have found that, when the right conditions are met, plasma can actually be suspended, floating due to electromagnetic interactions. This levitation occurs when intense magnetic fields engage with the plasma's charged particles, effectively trapping them and holding the plasma steady in midair. The real intrigue begins as scientists try to unravel the mechanisms that allow such clouds to remain hovering, seemingly unsupported. How exactly do electromagnetic fields stabilize the plasma, preventing it from collapsing or drifting away? And more importantly, what can this reveal about the underlying principles of physics, especially in high-energy environments? Some experts theorize that decoding the behavior of levitating plasma could transform how we produce and use energy. It might lead to significant progress in nuclear fusion, or even pave the way for futuristic propulsion systems. The implications are immense. What makes this mystery even more captivating is its potential. The idea that such technology could tap into the same forces that power stars and galaxies. Levitating plasma clouds push the boundaries of what we understand about matter and energy, reminding us that even amid cutting-edge research, profound mysteries still exist, waiting to be explored. The arrow of time paradox. We experience time moving from the past into the future, constantly sensing its progression. But what if that experience isn't as straightforward as it appears? What if the direction of time, what scientists call the arrow of time, is more complicated than we assume? The arrow of time paradox is among the most confounding puzzles in physics. It centers on the notion that time seems to have a clear direction. Events unfold in sequence: past, present, then future. We have memories of the past, but none of the future. We observe events like a glass falling and breaking, but never see it miraculously reassemble itself. This one-directional flow of time feels intuitive, yet it raises a profound question. Why does time appear to move only one way? Interestingly, the laws of physics, such as those governing motion or gravity, don't actually require time to have a preferred direction. These fundamental laws are time symmetric, meaning they work just as well if time were reversed. So why is our experience of time consistently forward? Why don't we ever perceive time rewinding, undoing decay and disorder? The leading explanation involves a concept known as entropy, which is a measure of disorder in a system. As time advances, systems tend to evolve from order to disorder. For example, solid ice melts into liquid water, or a clean room gradually becomes cluttered. This continual rise in entropy creates a kind of time arrow, pointing inexorably forward. But here's the curious twist. While the increase in entropy explains our experience of time's direction, it doesn't fully answer why entropy and time are so deeply connected in the first place. That's the heart of the arrow of time paradox. It remains an unsolved mystery that challenges our understanding of not just physics, but reality itself. Could it be that the flow of time is far more enigmatic than we currently realize? The true nature of time still eludes us, hinting at even deeper questions about the structure and origin of the universe. Quantized inertia theory. Imagine a theory that redefines the very fabric of the universe, one that questions the long-standing foundations of physics we've relied on for generations. This is the essence of the quantized inertia theory, a concept that could potentially reveal a concealed dimension of the cosmos. This theory was introduced by physicist Mike McCulloch in 2007. At its heart, quantized inertia presents a revolutionary view of inertia, the resistance an object has to a change in motion. Traditionally, physics links inertia directly to mass, making it a cornerstone of how things move. However, McCulloch suggested that inertia might be shaped not only by mass, but also by hidden energy fields in space. These include phenomena like cosmic dark energy and vacuum fluctuations, forces usually ignored in standard physical models. The real intrigue begins when McCulloch applied his theory to galactic behavior and the mechanics of space exploration. According to quantized inertia, objects traveling through space could be subject to a different kind of inertia. This could potentially account for anomalies like the rotation patterns of galaxies, which have long appeared to defy what current gravitational laws predict. These inconsistencies have baffled physicists for decades and led to the proposed existence of dark matter. Could quantized inertia offer a different answer to what drives these strange galactic behaviors? One that doesn't rely on the elusive dark matter? The theory even stretches into the realm of interstellar travel. If we could truly comprehend inertia at the quantum scale, could that knowledge lead to new propulsion technologies? Might we one day draw energy directly from the underlying structure of space? Though still considered speculative and not embraced by most of the physics community, quantized inertia prompts an unsettling but fascinating question. What if the true forces shaping our universe differ from everything we thought we knew? The enigma of quantized inertia remains. It challenges our grasp of spacetime and the very dynamics that govern existence. And in many ways, the quest to understand it is just getting started. Theory of everything. The theory of everything. In physics, we've uncovered essential laws and equations that accurately predict how planets move, how atoms behave, and even how the universe began. Yet, each of these laws only describes a piece of the overall picture. We use one set of rules for gravity and a completely different one for quantum mechanics, and they don't align. The theory of everything proposes that there exists a single, unified framework, a master equation that can explain all phenomena. Every force, every particle, every interaction, from the bending of space-time to the inner makeup of matter, would fall under this one comprehensive theory. But there's a challenge. After many decades of exploration, scientists still haven't discovered this ultimate formula. Einstein's theory of general relativity models gravity with remarkable accuracy. Meanwhile, quantum mechanics explains the bizarre and unpredictable behavior of subatomic particles. However, when we try to combine the two, like in the core of a black hole or at the very beginning of the universe, our calculations fall apart. Some of the boldest theories in modern physics, such as string theory, loop quantum gravity, and grand unified theories, offer possible solutions. Yet so far, none have been definitively proven. So, the mystery continues. Is the universe governed by one elegant underlying principle that we have yet to identify? Or is reality inherently fragmented? The theory of everything is not only about merging physical laws, it's about uncovering whether all existence follows a single, hidden blueprint, or if the last missing puzzle piece might never be found at all. Strange matter contagion hypothesis. Within the realm of theoretical physics lies a concept both chilling and fascinating, something known as the strange matter contagion hypothesis. Though it may sound like science fiction, the consequences it implies are alarmingly real and potentially catastrophic. This hypothesis proposes that a rare and mysterious substance called strange matter could propagate uncontrollably across the universe, converting everything it encounters. Strange matter is believed to be composed of strange quarks, a type of fundamental particle that only exists under extreme conditions, like those found in the ultra-dense cores of neutron stars. Unlike the ordinary matter we're familiar with, strange matter is theorized to be far more stable. In fact, some physicists speculate it could be more energetically favorable, and therefore more powerful, and possibly more dangerous than normal matter. The enigma deepens with the contagion aspect of the theory. What if strange matter could infect regular matter? Picture this. A tiny fragment of strange matter comes into contact with a particle or object. Rather than remaining isolated, it triggers a transformation, converting the ordinary matter into strange matter as well. Much like a virus, this chain reaction could ripple outward, converting one particle after another until entire objects, or even entire regions of space, are fundamentally altered. The implications are deeply unsettling. If such a transformation process occurred without limits, it could eventually devour all known matter, planets, stars, perhaps even entire galaxies, replacing it with an unfamiliar form of existence dictated by strange matter's unique properties and laws. Despite how ominous it sounds, this hypothesis has intrigued physicists who study the universe's most extreme environments. Could strange matter really exist? And more critically, could it spread? Or is this merely a theoretical possibility that nature never permits? The strange matter contagion hypothesis remains a deeply compelling mystery, one that challenges everything we think we know about matter, stability, and the fundamental workings of the universe. Cosmic inflation instability. In the world of physics lies a profound concept: cosmic inflation instability. At the dawn of time, something extraordinary unfolded. Within a tiny fraction of a second, the universe expanded at an incomprehensible speed. This moment, known as cosmic inflation, laid the foundation for all the structures we observe today. Yet, beneath this rapid expansion lies an unsettling enigma. Could the very mechanism that birthed the universe also threaten its stability? The theory of cosmic inflation proposes that immediately following the Big Bang, the universe underwent exponential growth, faster than the speed of light. This explosion of expansion ironed out irregularities, producing the large-scale uniformity seen in galaxies and cosmic structures today. It's a cornerstone of modern cosmology. However, there's a troubling complication. Some physicists suggest that inflation might not be inherently stable. In theory, the same inflationary process could give rise to a kind of instability in spacetime itself. Such instability could result in certain regions of the universe entering a renewed phase of rapid inflation. These surges might generate new pocket universes, or even distort the fabric of our own cosmos. Each of these pockets could emerge with entirely different physical constants, behaving independently from ours, suggesting that our universe might be just one bubble in a vast multiverse, like foam on a cosmic ocean. If this inflationary instability is real, it leads to a disturbing possibility. Could our own universe be affected? If the bubble we exist in were to collapse or shift, what would that mean for everything contained within it? Though highly theoretical at this point, the notion that the universe might not be entirely stable adds an ominous dimension to the story of cosmic inflation. The question of cosmic inflation instability is not only about decoding the origins of the universe. It's also about facing the possibility that our reality may be more delicate and more deeply entangled with the underlying mechanics of the cosmos than we've ever imagined. Theoretical magnetic monopoles. Consider a magnet, an ordinary object most people are familiar with. It always has two ends, a north pole and a south pole. But what if you could somehow find a magnet that has only one of those poles? A monopole, just a north or just a south, but not both. It sounds like a concept pulled straight from science fiction. Yet this possibility has fascinated physicists for over 100 years. It remains one of the most baffling puzzles in particle physics today. The idea behind magnetic monopoles is that they are particles carrying a single magnetic charge. either north or south, but never both together. That's unlike any magnet we've ever observed, where two poles are always present. If such particles are real, they would completely transform our understanding of electromagnetism, one of the fundamental forces that governs the universe. The mystery surrounding magnetic monopoles dates back to the 1930s, when physicist Paul Dirac first proposed that these particles could exist. According to Dirac, if monopoles were real, they could provide an elegant explanation for a major mystery: why electric charge comes in specific discrete units. That is, why electric charge is quantized and never appears in arbitrary amounts. Finding a monopole might offer profound insight into the deepest workings of reality, but despite decades of effort, no magnetic monopole has ever been detected. This lack of evidence raises important questions. Are monopoles just theoretical ideas with no real-world counterpart, or could they actually be out there somewhere in the cosmos, simply eluding discovery? Some scientists theorize that monopoles might only exist under extreme conditions, perhaps hidden in ultra-dense cores of stars, or possibly created in rare high-energy particle collisions. These extreme environments might be the only places in the universe capable of producing them. The search continues, and the allure of magnetic monopoles remains strong. Could these hypothetical particles be the key to unlocking new physics, uncovering previously hidden dimensions of reality? Until one is observed, the quest for the monopoles stands as one of the most profound unanswered questions in science, a mystery that, if solved, could completely reshape our understanding of magnetism and the fundamental forces that govern the cosmos. Universe's missing antimatter. By all accounts, the universe as we know it shouldn't exist, at least not in its current form, filled with stars, galaxies, and people. In the very first moments following the Big Bang, both matter and antimatter should have emerged in equal proportions. And when the two meet, they annihilate one another in an instant, releasing pure energy. This is among the most well understood interactions in all of physics. Given that matter and antimatter were created equally, logic tells us they should have canceled each other out entirely. Yet, that's not what happened. For reasons we still don't fully understand, there ended up being a slight surplus of matter. Not a lot, just one extra matter particle for every billion matter-antimatter pairs. But that tiny imbalance made all the difference. As the rest annihilated into energy, that leftover fraction of matter is what remained. It became everything, every planet, every star, every cell in your body, which leads us to the profound question: where did the antimatter go? Or more precisely, why did matter win out at all? This enigma is called the baryon asymmetry problem, and it strikes at the core of modern physics. Some laboratory experiments suggest that particles and their antimatter counterparts behave slightly differently, a phenomenon known as CP violation, charge parity violation. But what we've measured so far doesn't come close to accounting for the vast imbalance we observe today. Some physicists propose that undiscovered processes occurred during the Big Bang. Others hypothesize the existence of unknown particles or interactions that remain hidden from current instruments. There's even a bold idea that a parallel antimatter universe might exist, completely separate from our own, beyond all contact. For now, though, we're left staring at a universe that, by all normal reasoning, should have vanished in a flash of energy, but didn't. The absence of antimatter isn't just a physics riddle. It's a humbling sign that everything we are and everything we see is balanced on a mystery science has yet to solve. Anomalous magnetic dipole moments. Among the most essential ideas in physics is the magnetic dipole moment, a property that reflects a particle's magnetic characteristics. It's this quality that gives particles like electrons their spin, allowing them to respond to magnetic fields in ways we expect. But what if this behavior isn't quite as straightforward as we've long believed? What if a particle's magnetic dipole moment behaves in a way that defies explanation? This is the enigma behind what scientists call anomalous magnetic dipole moments. Back in the 1940s, physicists began using the framework of quantum mechanics to calculate what the magnetic dipole moment of an electron should be. The predicted value matched early experiments, seemingly validating the theory. However, in the 1990s, a far more accurate experiment delivered a surprising result. The measured magnetic moment was slightly different from what theory had predicted. That tiny inconsistency, this anomalous magnetic dipole moment, wasn't merely a case of experimental error. Instead, it hinted at the possibility that some unknown influence was affecting how electrons behave. Some scientists now believe that this anomaly might be caused by interactions with new particles or undiscovered forces existing within the quantum realm. Could it be that electrons are engaging with some invisible entity or force that we haven't yet been able to observe? The mystery has only grown as further experiments have been carried out. Each new test seems to strengthen the idea that our current models of particle physics are missing a crucial component. Could this tiny irregularity be the first evidence of a more profound layer of reality, hidden beyond what we currently understand? The anomalous magnetic dipole moment may represent one of the most subtle deviations ever recorded, but it holds the potential to trigger massive breakthroughs, possibly even reshaping how we think about the fundamental forces of the cosmos. It remains an open question, a problem still waiting for resolution. And as the search for answers continues, we may find that this small anomaly leads us to revolutionary discoveries, rewriting the very foundation of modern physics. Dark flow. Across the vast reaches of the cosmos, galaxies are typically found drifting apart, receding from one another as the universe expands. But what if an unknown force was steering them in a direction we didn't anticipate? This puzzling movement is what we now refer to as dark flow. First detected in 2008, dark flow was observed when scientists noticed that certain galaxies, particularly those located in the most distant areas of the observable universe, weren't merely participating in the uniform expansion of space. Instead, they appeared to be moving with purpose, drawn toward a specific region in space. This directional motion didn't line up with what we'd expect from standard models of cosmic expansion, leaving researchers puzzled. What could possibly be behind this unusual drift? What's especially intriguing about dark flow is that it doesn't appear to be influenced by any familiar force, not even gravity from known galaxies or clusters in the vicinity. Some scientists have proposed that it might signal the presence of a massive structure, one so distant and vast that it remains undetectable with our current instruments, exerting an immense pull. This unseen entity might be a supermassive galaxy cluster or some other enormous cosmic formation, and it directly challenges our conventional understanding of the universe on its largest scales. Adding to the mystery, dark flow may imply the existence of realms beyond the observable universe, regions we cannot currently explore or even detect. That possibility alone is staggering. Could these hidden areas contain unknown forces, undiscovered galaxies, or perhaps even entire universes? The phenomenon of dark flow forces us to confront the possibility that there's far more to the universe than what we can presently see. It points to a force we don't yet comprehend, one that's dragging galaxies along paths that defy explanation. As researchers continue to investigate this cosmic riddle, one thing becomes increasingly clear. The universe still guards many secrets, waiting to be uncovered.